Hello again. Light as a particle. Let's have a look at photons. I mentioned them a lot in the last video, and I've mentioned them before when we looked at electromagnetic spectrum. Let's learn a little bit more about them. Now, photons, sometimes called quantum, but all electromagnetic radiation, which includes light, comes in small discrete packets of energy called photons or quantum, and that's what Planck worked on and discovered. And as we mentioned before, he came up with the equation E equals hf, where E is the energy of the photon in joules, h is Planck's constant, which is a very small number, 6.63 times by 10 to the minus 34, and so each photon contains a minute amount of energy, because if we multiply that number by the frequency in hertz, we get the energy in joules. But the thing is, there's a lot of them, and so even though they carry a minute amount of energy, there's a lot of them. Now, since electromagnetic radiation is controlled by the equation C equals lambda F, or we've also said V, where C represents the speed of light, of course, lambda is its wavelength, and that's its frequency, we can combine or rewrite E equals hf by substituting in C divided by lambda. And so we get E equals hf equals hc on lambda. And so if we know Planck's constant, the speed of light, and the wavelength, we can work out the energy of the photon. So the shorter the wavelength, and therefore the higher the frequency, the greater the energy of each quantum. So remember, we said when we were looking at the electromagnetic spectrum, if you think of it, you have violet at one end and red at the other end, and infrared is just the heat that you get off that you can feel, whereas violet, and that's a long wavelength, whereas you go shorter and shorter the wavelength, you go into violet, and then you go ultraviolet, and that's the sort of stuff that can give you sunburn and skin cancer, which is not good for you. So the energy of the photons related to the wavelength and related to the frequency. Quantum is a very, very small amount of energy. So the quantum for red light, so one photon of red light, is around 2 EVs. And 1 EV is 1.6 times by 10 to the minus 19 joules. So let's have a look. What is the energy of a photon of yellow light, which has a wavelength of 554 nanometers? So we've got to convert the nanometers to meters, of course. First of all, we have to find the frequency. So we get the speed of light, 3 times by 10 to the 8 divided by the frequency, and then we get that in hertz, and then we put it into E equals hf. Now we could have gone straight into our previous formula that we had back here. Whoops, there it is. Okay, we could have just put it straight into here and got E as well, but they're doing it in 2 steps, which is not a problem. And so they've used their Planck's constant, the frequency, and then the energy in joules. Not much. Now in the next video, we'll actually be looking at the photoelectric effect. See you.